session will be CSS Minification via constraint solving, and Matthew Haig will be giving the talk.
Okay, thank you very much. So I'd like to just start off by explaining this paper. So this is not a proper paper. It's a paper that's recently been accepted to top class.
Still a proper tape of paper.
Capacity. So I'd like to just thank the organizers of POPL for finding some space to slot us in. Okay, so this is a joint work with Anthony Lynn and Chino Hong at Oxford, and I myself am at Royal Holloway. So in contrast to the other talks, this is about website optimization. So Firefox had a problem, that's nice. Appropriately enough. So I thought I would start off just by, most of us probably know how websites work. We've edited our own homepage, but I just wanted to point out some features that are of interest for us today. So here's a picture of a website, and here's the code that you've probably written a bit of yourself. There are three main components. One of them is the document object model, or the DOM tree. And what this is it's a tree structure that contains all of the elements in your page. So here you see you have a heading that contains the title. A sibling of the heading is the image. And these elements, they have a bit of extra information. So the source is superman.jpg, and we have this class, and we're saying that this class is a side image. This gives a bit of extra information, which we're going to use a bit later on. You can see this div here, info, it has some children. It has 2 children, in fact. So it's a tree structure, and that's the main thing we're interested in. The next part I want to just briefly mention is the kind of dynamic components. So websites now are not static, they're dynamic, and in fact, they use JavaScript, and they use increasingly complex JavaScript libraries. And essentially what I want to say here is this is a difficult problem, and we want to ignore it as much as possible. The key point is that you can't really tell in advance what kind of trees you're going to be dealing with. So the final part, and the one that's most interesting to us, is the CSS style sheet, which is, as you might imagine, it tells you how this web page is going to look. It gives you the style information. So here is the style sheet. It consists of a sequence of rules. So there are 4 of them here. Each line is a rule, and each rule has 2 components. So outside the bracket braces, we have the selector. And what the selector does is it picks out elements on the page. And inside the brackets, we have some properties that say what that element should look like. So you can see our image that's on the side should actually float on the left. And our info section should be gray. So these last 2 actually demonstrate that these selectors can get a bit complicated. They don't just sort of pick out the tags. They actually allow you to move around this tree structure. So this is going to match any name element that's the child of an info element. And this is any date that's the child of an info. So you can move around the tree, and these selectors can get quite complicated. Okay, so that's CSS. What are we going to do with it? So we're actually interested in shrinking this. So let me move that up. Can I show that? No. Okay, that's hidden. So what we're going to do is we're going to introduce a kind of a precise semantical model of the latest stable CSS standard. And we're going to use that to do some optimization. We're going to try and minimize these style sheets as much as possible. And this is going to be a tool based on constraint solving. And written down here, I'm saying that we've done some experiments on large-scale CSS, proper industrial style sheets. And they show that we actually have some gains. Okay, so what do I mean? Why are we optimizing style sheets? So if you go to the web and you try and poke around Amazon, say Amazon's website, and look at what style sheets they're using, you get back this horrible kind of wall of text. And this is standard. Every website, you'll end up with something like this. And what they're doing is they're trying to shrink all of the information into as little space as possible. The idea being that the quicker you can deliver your web page, the more of people's attention you're going to retain, and the more money you'll make somehow. So minification, it's widely adopted. It's pretty much standard. And what it's doing is quite cheap. It's simple syntactic transformations that should not change what your web page looks like. So the most obvious thing it does is it takes all of these spaces that make it look nice and throws them away. We don't really need them. It can also do other rewrites. So this color here, in its full hex code glory, is actually just red. So it takes 3 characters to write red, 7 characters to write hex code, so we'll write red instead. And there are lots of tools around, so CSS Nano, Minify, and so on. And what these do is they have a big bag of tricks, of little rewrites they can make to save a few bytes here and there, and hopefully shrink down your style sheet. So these syntactic the rewrites are nice enough, but there's only so far you can go. And what we're kind of interested in, say, as researchers, is can we do something a bit smarter and increase the savings in the process? So one particular technique we're going to focus on is something called rule merging, where we're going to look for common parts of these rules, and we're going to try and combine them into a single rule that has all the same information, which saves us some more space. So here we have two rules. It says the A should be red and the B should be red. So those both say the same thing. We can merge them together into a single rule that says anything that's A and anything should be red. So we've saved ourselves repeating the word color red twice here. And some tools, they do this already, where it's not our idea. So CSS Nano, one of the minifiers I mentioned earlier, it tries to do a bit of this, but it's still operating on quite a syntactic level, so it can only do it in a very restricted sense. And I'll get onto a bit why it's, and later in the talk, I'll try and tell you why this is actually a bit more complicated. So the kind of main people who try and do this are more research-based. So there's Manzunanian, I think, who has a tool called CSS Analyzer, and he does this kind of merging, but he only guarantees that he won't break your style sheet as long as you tell him exactly which trees you want to maintain the correctness with respect to. As I mentioned, this can be impossible to know because of the scripting component. So this is unsound in general. There's also some work by Pierre Geneves et al. And they do kind of sound rewriting, but they only have a very partial semantics of the CSS. So what the point is, what we're trying to do is try and do this general merging in its full generality based on a full understanding of the CSS files and the structure and the kind of selectors that are involved. Okay, so why is this rule merging so difficult? So here's an example to illustrate it. So here we have a style sheet with three rules. We say A is red, B is green, and C is also red. So at this point, you might say, aha, I've spotted that these two rules, the A and the C, are both pretty much the same. Let's combine them and save ourselves some bytes. And you might do this. You'll say .A.C is red and .B is green. And this looks nice so far until your web developer does something like this and gives you an element that's a paragraph, but it doesn't just have one class anymore. This guy has two classes. It's both class B and class C. So this instantly creates a problem because we're saying here that B should be green and here that C should be red. So there has to be some way of resolving this conflict. And there is a systematic way. And what it turns out is that actually the order matters. So here, the red appears last, so it prints it in red. But because we combine these rules, we change the order, and now green comes last, so the color changed to green. So when we look at these style sheets and we think about them, we find that there's kind of some ordering dependency that needs to be maintained when we're shuffling things around. And this isn't just a contrived example. So if you go to CSS Nano's webpage, you'll pretty quickly find in July this year, someone reported this bug. Here's one of their optimizations, declaration sorter. You can tell it does some reordering because it's sorting. And their reordering is breaking the style sheets. And this web developer used this tool, found it was breaking the website and reported it. And we have 8 people here, 48 comments, a kind of a long discussion to fix this problem. So what are our contributions? So the first thing we've done is we've provided quite a solid theoretical foundation for all of this. We're not just working on syntactic level, we've looked into everything. So in particular, these selectors I showed you, they can get quite complicated. So we've worked out the kind of semantics of these. We've also worked out exactly when we need to worry about these orderings. So this kind of formal model CSS files refers to kind of an ordering semantics. So it's nice to have these semantics, but obviously we want to use them. So this leads to a bunch of computational problems. So how can we construct these ordered dependencies? So we have algorithms that can do this, which entail actually finding out when there might be a conflict. So when might two selectors end up fighting over the same element? So this is kind of a logic decision problem. Also, we solve that, and we have the complexity in our paper. And this is all for CSS version 3, which is the most recent stable specification. You might have seen CSS 4 is starting to be developed, but during our work, this was not stable, so we have not looked at it. The kind of second aspect of our contributions is a tool for minimizing CSS. So we've taken these semantics and we're making use of them to do this rule merging operation. We have this very simple loop where we go around, We greedily just look for the best merging opportunity, so how can we combine things to make the biggest saving? We apply that, and then we go around the loop again. And we just keep doing this for as long as you're willing to let the tool run. We've done some experiments. So to actually find this best merging, it's not such a straightforward problem. It's actually an optimization problem itself. And we reduce it to a max-sat problem. So if you know constraint solving, this is looking for the best solution to a problem. And we have an experimental evaluation based on real, actual industrial CSS files, and we compare with the other minifiers and show that this actually does provide some new optimizations. Okay, so in the remaining sort of 8 minutes, I'm going to talk about, first of all, a bit more about this ordering. So why is it complicated? Why are CSS selectors complicated? And then a little bit about how we go about finding the best kind of merging opportunity we can find. So let's look again at the ordering. So if we remember the example I had before, the problem was that we had kind of a dependency between this selector here, .b green, and this selector here, .c red, which was based on the fact that these two selectors here could end up matching the same node. It could be a conflict that occurred. So very roughly, if this conflict can occur, we should make sure not to reorder the selectors. The real rules are actually much more complicated, but they're complicated in a sort of hard-to-explain way, but very easy to implement way. But however, if we actually think about selectors in their full generality, they don't look as nice and simple as we had before. They look kind of like this. So if you want to say, can these two selectors match the same node, this is a much harder question to answer. In this case, the answer is yes, but to answer it, we actually have to look at a logic that has several features. So first, it's kind of a modal logic over trees, so this bit's kind of navigating around the tree. It has some integer reasoning, so we're talking about the nth child or not the nth child, modular a factor of n. And we have some string reasoning, so we're saying the source contains the word file and it ends with .pdf. So we've got to reason about strings as well. So this kind of looks pretty negative, and you start to worry that this logic is probably hopeless. But fortunately, this turns out to be NP complete. So it's actually much more manageable than we thought it would be. So what we show is that this is NP complete, and moreover, we can reduce this to SMT solving. So we can throw this at Z3, and it's generally pretty quick. So we can construct the kind of ordering dependencies in pretty reasonable time. Okay, so that's the kind of selector part. So what about merging opportunities? So I said that we reduced to max-sat. So what max-sat does is you give it a bunch of constraints, and you want to look for a solution to these constraints that's somehow the best. So in particular, what we're looking for is a rule that we're going to put somewhere in our file that combines other parts of the existing style sheet. We want to know where to put it. And the second part of the max-sat problem is kind of a score that says how good your solution is. So in particular, the better a solution is means the more of the other parts of the file it uses. So by adding this new rule, we can delete lots of other parts that are now made redundant. So we're looking for the biggest solution to this problem. Now, if you know about max-sat, you'll probably realize that this is not such a hard thing to encode straight away, because you take other parts of the file. So let's introduce some variables representing which parts of the file you're going to use. Let's have some saying where it's going to go. And then let's have some constraints that say, do not break any orderings, and some more that kind of somehow count how many savings you're making. This is not too difficult if you're familiar with max-sat, but it doesn't work at all. It's really hopeless. I don't mean that it doesn't work in that it's a bit slow. I mean that you can have, the examples we tried were like 10 lines, 15 lines, and we could wait days and not get an answer. So it really doesn't work. So we had to come up with a better way of encoding it. So in the end, we settled on something that you call maximal orderable bytecleats. And this coding actually allows us to get responses on quite large style sheets in a reasonable amount of time and make some progress. However, because I really only have 18 minutes, I sort of just say this is a whole rabbit hole worth exploring. Okay, so what about the experiments? So we implemented this and we tested it out to see if it works. We tested this on 71 CSS files in total. And these are ranged between up to 300 kilobytes, on average about 50. This is kind of average for the web, and we sort of know this because we took 40 websites and all of them, and 40 websites that include all of the 20 most popular websites. So anything you could think of, like Amazon, Google, Facebook and things like that. All of those are in there, and we've used the CSS that they're delivering. And we compared it with as many minifiers as we could find. But a key point I want to make is that we're actually not doing the same thing. We're not doing the syntactic rewrite. We're doing a whole different kind of optimization. So really, we're doing a complementary approach. We let the tool run for up to 30 minutes. But I'm going to show you a slide later just to prove that 30 minutes is not cherry-picked. It's just a number that we plucked out of the air before we started. And the key point is you can stop at any point and just take however much progress it's made at that point. OK, so these are the results. So there are kind of two halves to this result. So on this side, we have the result of just running the minifiers. So this one's ours, and this one is the other minifying tools. And you see that we're doing kind of a little bit better. But I don't particularly like that side of the graph because I think it's a bit unfair because we had to go to the web and get this style sheet. We didn't have the original development style sheet. So that style sheet had already been kind of minified. So all these guys had their tricks kind of taken away from them already. So it's a bit unfair. I do, however, like this side of the graph because this is what happens when you combine them. This is, say, run a minifier and then apply our rule merging on top of that. And you'll see that what we're actually doing is we're genuinely boosting the savings made by these tools. We found an optimization that is actually new. It's not just repeating what they're doing in a more complicated way. So if you'd like to see some figures, then here are kind of some. So on average, we kind of be able to combine these to get 6%, going up from like 3.8%. So we're kind of boosting them still. In the third quartile, we have these numbers. And if we want to kind of something to put on our PR copy, we can compare the ratio of the savings we make compared to the ratio the minifiers are making, and we can find that we're doing kind of a lot better with some nice odds ratio numbers. Okay, so what about, so this was my graph about the timeout. So because we're going around this loop where we're repeatedly applying refactorings or mergings, you'll see that actually most of the savings, because it's a greedy loop, it takes the good ones first. So most of the savings occur kind of in the first initial phase. And then we get this long tail where we're just kind of grinding away with diminishing returns. So really, we could have run the tool for like 2 or 3 minutes and got the same results. OK, so where does this leave us? So kind of the first perspectives on this are that our tool kind of works OK. It's a new optimization that improves on existing minifiers. But I think the nice thing is that it's actually a new one that we can combine with existing minifiers. That's kind of the more important thing to do. But one other nice thing, I think probably the main contribution in my mind, is that we've built these foundations upon which new techniques can be tried. We no longer have to restrict ourselves just to syntactic rewrites. We actually have a formal basis to try out all sorts of crazy things that we can think of. In particular, one thing I didn't mention is about gzip. So usually when you distribute these kind of files, they go through a compression process first. Whereas our experiments, we only looked at raw file size, which is very naive. So really, what we would be interested in is how big that file is after we've done the gzip compression. So really, we want to introduce kind of rewrites and shuffling around that actually improves gzip. And this is why CSS Nano was doing this declaration sorting and causing problems in doing it, because it wanted to improve the gzip thing. So it'd be nice, kind of an avenue of future work, to actually look at how to optimize the gzip encoding. And we now have the foundational tools on which we can build to do that. OK, so that's everything. So thank you.
Very nice work. So I have 2 questions. So one, I perhaps missed it, but do you support the important construct?
Yes, yeah.
OK.
Yeah.
And the other question is that there is now some work on, this is Martin Renard, there's a paper now on essentially optimizing, this is for LED displays, but there are cases in which you can slightly change colors and the picture will look the same and you save energy. And here energy for you is space. Have you thought about having cases in which you slightly make a different CSS files, but they look still pretty fine?
We haven't thought about that, no, but that could be in the kind of things you can do.
OK, other questions? We have a question on Slido. Does your semantics give any guidance for the design of CSS itself?
That's a good question, actually. So we kind of did think about that. So if we look at CSS 4, so from what I remember, some of those constructs look like you're going to go up to pspace at least to do this kind of collision detection. So maybe this is one of those things where you might want to think, do I really want that? Does it bother me that I've now got a p space or perhaps undecidable logic? So it could give some guidance in that way.
Other questions? Okay, let's call it a wrap.